Good morning, welcome you to this session. Today I will first solve few example problems which is centered around the discussion that we had in the last 2 or 3 preceding sessions. So, let us start with that example problems, then I will start a new section as I told earlier, that availability, the concept of availability, but before that we will go through this example problem. Please see that. First example is this one: a heat engine operates between the maximum and minimum temperatures of 671 degrees Celsius and 60 degrees Celsius respectively, with an efficiency of 50% of the appropriate Carnot's efficiency. That means the heat engine is prescribed which is operating between the two thermal reservoirs 671 degrees Celsius and 60 degrees Celsius, but it is an irreversible heat engine where the efficiency is 50% of the appropriate Carnot's efficiency. Well, then this heat engine drives the heat pump which uses river water at 4.4 degrees Celsius. That means from this temperature of 4.4 degrees Celsius, that of the river water, heat is being extracted by the heat pump to heat a block of flats where the heat is being delivered, in which the temperature is to be maintained at 21.1 degrees Celsius. That means for heat pump, the two thermal reservoirs are 4.4 degrees Celsius where from heat is being taken and 21.1 degrees Celsius where the heat is being delivered. So, from low to high temperature, this is because the heat pump operates like that, where it takes work from surroundings, that is in this problem from this heat engine which is working between these two temperatures. This is the definition of the problem. Apart from that, there is another thing: assuming that a temperature difference of 11.1 degrees Celsius exists between the working fluid, which is very important, and the river water on the one hand and the required room temperature on the other. That means, when the heat pump operates, the system temperature, the working system temperature, the system executing the cycle, when it takes heat is not 4.4 degree. Similarly, when it delivers heat, it is not 21.1 degree. There is a difference between the temperature of the working system in the heat pump with the thermal reservoirs on both the sides is 11.1 degrees Celsius. Assuming that a temperature difference of 11.1 degrees Celsius exists between the working fluid and the river water on the one hand and the required room temperature on the other, and assuming the heat pump to operate on the reversed Carnot cycle, but with a COP of 50% of the ideal COP. A reverse Carnot cycle means an ideal or a reversible heat pump. So, this heat pump is an irreversible heat pump, and that you can very well recognize that there is a irreversible heat transfer because of the finite temperature difference of 11.1 degrees Celsius. This is one of the reasons. So, the COP of this heat pump is 50% of the ideal COP. So, if this be the case, we have to find out the heat input to the engine per unit heat output from the heat pump. Well, the heat input to the engine per unit heat output from the heat pump. And what would be the required heat input to the engine? That means the same thing, heat input to the engine per unit heat output, if the required temperature difference in the heat pump is reduced from 11.1 degrees Celsius to 5 degree. That means this one is reduced to 5 degree. That means this is the difference in temperature on both the sides of the reservoirs. That means between the working fluid and both the reservoirs at 4.4 degrees Celsius and 21.1 degrees Celsius. So, this is the problem. So, now let us see how we can solve this problem. Now, the problem again, if it is defined, is like this: there is a source temperature for a heat engine. What is this? This is 671 degrees Celsius. That means it will be in absolute 671 plus 273 is equal to what? 944. 994, I am sorry, 994 K. 671 944, I am sorry, 944 K, very good, 944 K, very good. And this heat engine operates, this is a heat engine on a cycle, thermodynamic cycle, and it delivers heat to the temperature. What is that temperature? 60 degrees Celsius. That means 60 plus 273, I am adding 273. As you know, this is the Kelvin conversion from Celsius to Kelvin, that will be how much? 333 K, and this heat engine delivers work. Now, this is the heat input Q1, let us see. Let the heat rejected out of the engine is Q. So, W is delivered, which is definitely is equal to Q1 minus Q2. But this drives a heat pump, that is the problem. This is the heat pump which operates on a reverse cycle, and here the temperature are like this, from which it takes the heat, that is 4.4, 4.4, the figures are not conducive, 273, what is this? 277.4 K, and what is this temperature where heat is being, let this heat taken is, let that is taken be Q3, let this be Q3 and let this be Q4. Okay. So, what is this temperature to which heat is being delivered is 21.1 plus 273, what is this? 294.1 K. All right. Now, what we have to find out? We have to find out what is Q1 by Q4, that is to be found out, Q1 by Q4. Achha, now, you see the efficiency of this engine is 50% of the Carnot's efficiency. So, therefore, work, now what is work here? Work is eta of this engine, eta engine into Q1. So, I always try to induce the parameter Q1. So, I will use the formula which always involves Q1, because we have to find out Q1 by Q4. So, my first job is to find out eta engine. What is eta engine then? Eta engine is 50% of the Carnot's engine efficiency. What is Carnot's efficiency? 1 minus 333. We know the Carnot cycle, if this could have been a reversible heat engine. So, efficiency could be equal to, that is the Carnot's efficiency, 1 minus T2, that is the temperature of the thermal reservoir where heat is rejected, divided by T1, the thermal temperature in thermodynamic absolute scale of the reservoir where heat is being taken, from where heat is being taken. That means 331 divided by 333, sorry, divided by 944. And if you equate this value, this will come to 0.32. So, therefore, we can write W is equal to 0.32 Q1. All right. Now, this W drives the heat pump. So, therefore, what will be Q4? Now, Q4 by W is the COP. So, Q4 is W into COP of heat pump. Okay. This is all right. Q4 is W into COP of heat pump, because this COP of heat pump is defined as heat delivered to the high temperature reservoir where this machine is acting as an heat pump. So, this is the output parameter of our concern, divided by the input to the machine, which is the work. Now, what is the COP of the heat pump? But here one catch is that there is a thermal irreversibility. That means, the temperature of the working fluid here and temperature of the working fluid, let this temperature is T4, let this temperature of T3. Neither T4 equals to 294.1 K nor T3 equals to 277.4 K. So, what is first T3? There is a temperature difference of 11.1 degrees Celsius, that it is defined in the problem. So, heat is coming from here, that means this temperature will be less than this, which means, sorry, 277, that means here I write T3 is equal to 277.4 minus 11.1. What is this value? 266.3. Very good. Similarly, what is T4? T4 heat will go from here, so that will be 294.1 plus 11.1. What is this value? Please tell me.
62.
Please.
Would it be the other way around because the work is being inputted?
Yes.
The heat will flow from a lower temperature to a higher
High temperature, yes. Yes. Heat is flowing from lower temperature. Heat has to first be transferred to the working system here. So working system will have to be a lower temperature to take the heat in natural process of heat transfer. Heat is ultimately transferred from lower to higher temperature. But first heat has to be transferred to this fluid, then it will transfer from heat. There are other processes going on. You see, one of the processes is the heat taken up from this reservoir. One of other processes is that heat given by the heat pump to this reservoir. So when heat addition is taking place to the working fluid of the heat pump working fluid is of this temperature, so that this temperature gradient can transfer heat from this temperature to the working fluid or working system. This is one of the processes of the thermodynamic cycle executed by the system. Similarly, one of the processes in the thermodynamic cycle is the heat rejection by the system, working system, which has to reject heat to this reservoir. So this temperature has to be higher than this temperature. So this way we will have to set. So what is this temperature? 305.2 K. So it is clear then? Okay. Then now we have to find out what is the ideal. Now COP of the heat pump, COP of the heat pump is equals to 0.5 into COP of the ideal heat pump. What is the COP of the ideal heat pump? That can be written as, now COP of the ideal heat pump, we have to consider a heat pump which is ideal, then the reservoir chosen by the heat pump has to be of this temperature, so that it can reject heat to this temperature. Similarly, it can take heat to this temperature. So the heat pump will be a reversible one when the external irreversibilities will be reduced. That means the temperature of the reservoir should be like this, so that we can write this 305.2 divided by 305.2 minus 266.3. So this is the ideal COP. Why this COP is less? Because of internal irreversibility and the external irreversibilities because of the finite temperature difference heat transfer. So this comes out to be COP 3.93. Then the problem becomes extremely simple. Then Q4 is W 3.93 W, because this is the COP of the heat pump. Now again W is 0.32 Q1, so Q4 is equal to 0.32 into 3.93 Q1, and which gives Q1 by Q4 is 1 by 0.32 into 3.93 equals to 0. This is the answer, 79 kilojoule per kilojoule. This kilojoule per kilojoule means kilojoule of heat input per kilojoule of heat output. You may write it or may not write it, because this quantity is unitless. That means this is the amount of heat delivered to the heat engine per unit amount of heat delivered to the block of flats by the heat pump. Okay. Next problem. Next problem is also very simple but interesting problem. This is relating to the entropy change. A very simple problem but with entropy change. An electric current of 10 ampere is maintained for 1 second in a resistor of 25 ohms, while the temperature of the resistor is maintained at 27 degrees Celsius. When an electric current is passed through a resistor which is having some resistance, the heat is generated. Sorry, I will not tell that heat is generated. You know, heat is an energy which comes in transit. Its internal energy is increased. So its temperature should increase, but temperature of the resistor is maintained at 27 degrees Celsius in this problem. That means this resistor is cooled in such a way that the generation of internal energy because of this electric current must equal to the energy out of the this resistor, so that temperature is maintained at 27 degrees Celsius. This is very important in this problem, that while the temperature of the resistor is maintained at 27 degrees Celsius, that means the temperature is constant for the resistor while the current is passed through this during a time of 1 second, and that temperature is 27 degrees Celsius. For this, what is the entropy change of the resistor? First part. B, what is the entropy change of the universe? Second part. Now, you see the same current is maintained for the same resistor. Now, this thing is that, but now thermally insulated. Now, the resistor is thermally insulated. That means, no heat is allowed to flow from the resistor, which while allowing a current to flow for some time and it has a resistance may increase its temperature, but heat is not being allowed to flow out of the resistor. Now, the resistor's initial temperature is 27 degrees Celsius. So, initial temperature is 27 degrees. If the resistor has a mass of 0.1 kg and a specific heat of 0.84 kilojoule per kg K, this is the unit of specific heat as you know, find what is the entropy change of the resistor and that of the universe. So, we have to find out what is the entropy change of the resistor and what is the entropy change of the universe in both the cases. One case the resistor is not insulated, rather it is cooled simultaneously while the current is flowing through it, it gets hot and it is cooled, so that temperature remains constant, and in other case it is not cooled, thermally insulated, so the temperature will increase. Its initial temperature is 27 degrees Celsius, its mass and specific heat is given. But one thing is missing in this problem. Whenever you are asked in any problem to find out the entropy change of the universe, so a reference, so to find out the entropy change of the universe, you have to know what is the surrounding temperature, which is very important. You understand what is the surrounding temperature? Surrounding temperature, you have to take the surrounding temperature which is not, but how then you can equate the entropy change of the surrounding? Surrounding temperature equals to 27 degrees Celsius, which is very important for this problem. If it is not mentioned, you can consider, you can take any value of the surrounding temperature, but it should be mentioned. Another thing which has not been mentioned in this problem, the way I have taken it, the type is not typed, that for this resistor consider the change in internal energy is given by specific heat of the resistors time the delta T. This is another important thing, that the change in internal energy of the resistor equals to specific heat times the delta T, okay, that is the temperature difference. So, these two will be required for solving this problem. Now, let us find out the first one. First one is what? There is an electrical resistor through which an electrical current is flowing because of some potential difference applied across the resistor. So, now the resistor is maintained at constant temperature, which means there is a heat transfer from the resistor. In this case, I can use this resistor as a system. I can represent the resistor as a system. Now, you tell me when the electrical current is allowed to flow through this resistor, which has a resistance R, there is a potential difference across the resistor, which means from thermodynamic viewpoint that electrical work is being transferred into the system, W electrical. And since the temperature is maintained constant, means some heat is also being coming out of this system, Q. So, this is the problem from first point, first law of thermodynamics, that resistor as a system receives electrical work and rejects heat to the surrounding, which is at a temperature of 27 degree Celsius. Okay. Now, if you consider the problem like this, what we have to find out? Delta S universe. Delta S universe. What we know that delta S universe, first part of the problem, A and B, A and B. Oh, we have to find out not only delta S universe, we will have to find out delta S system also. Okay. One thing is that if we have to find out delta S universe, you have to find out both delta S system and delta S surrounding. That is why it automatically comes delta S universe is delta S system, well, plus change in entropy of the surroundings. Well, now you see, in this case, what is the delta S system? Delta S system is 0. Why? Because resistor is at the same state, the steady state. So, no property is changed for the resistor. Now, if I write the first law of thermodynamics, I can write Q is equal to delta U plus W electrical. Since resistor is maintained at constant temperature, and if this relationship is given that delta U is related like this. So, when the temperature remains constant, that means delta T is 0. So, delta U is also 0. This has to be known. Otherwise, the question will come that how do we know that if the temperature remains constant, the internal energy also remains constant. So, we have to know this. So, that we can write that Q is equal to W electrical. So, what is the electrical work transfer? It is the voltage difference times the current, but voltage difference is not given. We can relate this in terms of resistance also with the use of Ohm's law, that you obviously know. So, one can write I square into R. That is the electrical work which is being transferred. So, what is happening physically, you see, this electrical work is transferred to the system, and because of electrical irreversibility, this electrical work is being converted into internal energy first. Then immediately the heat is being coming out because of the increase in the internal energy, which is because of the electrical dissipation of this electrical work, and immediately the heat will come, so that internal energy is restored to its initial value. So, this is the steps. So, therefore, in the system the electrical work is ultimately coming out in the form of heat to the surroundings. So, this is the electrical work. So, this becomes is equal to what? This becomes 10 amperes, that means 100 into 25. Please T, very good, very good, I am very happy. So, I am very happy. 25, what is the unit of it? What is the unit of it? I square R T joule, where I is ampere, R is in ohms, T is the duration. Okay, very good. Then it gives the amount of energy. It is for 1 second. So, as far as the result is considered, if you do not write T, it will be same, but it is definitely conceptually wrong, because I is the ampere with that rate is there. So, therefore, this will imply the power. So, you have to multiply with time. Very good. So, this is the Q. So, therefore, delta S system is 0. So, delta S universe is delta S surrounding. So, what is this? So, therefore, we can write delta S universe becomes equal to delta S surroundings. What is this? Surroundings receives heat at a constant temperature. So, this will be a positive quantity. Any problem? Please.
So, how can we consider that delta S system is 0? Because
yes, I am answering this question, but before that, here one thing, when you write this thing, so Q and W, though numerically all right, but you have to follow the sign convention. Here this electrical work is negative, Q is positive. So, therefore, we can write that it is minus. So, that Q will come minus, which means that heat is coming out from the system. With reference to the system is minus. So, with reference to the surrounding, it is a heat which is taken by the surrounding. So, delta S surrounding is positive. So, that is why delta S universe is positive, and that value becomes equal to how much? That value is 8.33 joule. We have already solved the problem, joule per Kelvin, joule per Kelvin, 8.33 joule per Kelvin. Okay, all right. Now, what is your question?
So, I asked, sir, how can we understand that delta S system is 0?
Delta S system is 0. I tell you that it is written that delta U is C delta T. This is given in the problem. Clear? Why you assume? Delta T is 0. So, delta U is 0. All right. So, delta U is the property, U is the property, delta U is 0. Okay. That means all the properties remain same. That is, this resistor is at steady state, the temperature remains same, its internal energy also remains same. That means these all other properties remain same. That means it is at a fixed state, that is known as steady state. So, entropy is a point function, so entropy remains same.
But, sir, we can consider that there is a exchange of heat.
Sir, there is delta Q.
So, it gives heat and it takes work. Not that always a system gives heat or takes heat, its entropy will remain same. If it gives heat and takes heat, at the same time it receives work interaction. We have to consider whether its property state point is changed or not. Not necessarily you take heat, there is a system which takes, there is a net heat transfer from the system. That means it gives heat or it takes heat. At the same time there is a net work transfer to the system. If these two things balance so that system remains at the fixed state, you understand, then its entropy will be same, entropy will not change. Do not consider that whenever there is a heat transfer that entropy will change. Entropy will change or not depend upon whether a system changes from one state to other state, because entropy is a property as a point function, state variable. So, you have understood. It has given some heat, so its entropy should have decreased, but at the same time it is taking work from the outside, so that its entropy will increase, that will balance. That means system is kept at a fixed state. Next problem it will be clear that there is no heat transfer, but still there is a change of entropy. This is because this state point is changed. It is not always that heat has to be taken in. I told you again categorically, I earlier also told that whenever there is a change of this state, there is an entropy change. That means that change is possible by a reversible process only by heat transfer. You understand? If you consider a process where the change of states is possible by no heat transfer in a reversible process, then only entropy will remain constant. That is an isentropic process. I gave that example. For example, you take water in a bath and stir it. The next problem, you heat the electrical wire or electrical conductor by insulating it. Its temperature increases, but there is no heat transfer, it is only work transfer. That work by virtue of some irreversibility. In case of stirring of paddle wheel or stirrer in a liquid, it is the mechanical irreversibility, friction which raises its temperature and change its state. In case of electrical resistance, insulated electrical resistance, it is the electrical irreversibility which changes this work into intermolecular energy and changes its state. So, in that case there is a change in entropy. Why? This is because the changed state can be connected by a reversible process which demanded heat. You understand? That means that change in temperature can be made, can be executed by addition of heat to the process, so that there is an entropy change. You understand? So, for a natural process, whether heat added or it is not added, that is not the question of change in entropy, whether the system state has changed or not, and that change in system is associated with a heat transfer process definitely by a reversible process if entropy change is there. But in an isentropic process there is a change of state by a system which is possible without heat interactions in a reversible way. That is why a reversible adiabatic process is an isentropic process. There may be two states which can be connected by a reversible adiabatic process, where heat transfer is 0 and the process itself is reversible, so there will be no entropy change. Okay, their entropy changes are due to irreversibilities. Clear? Now, next part of the problem is this. What is the next part of the problem? That next part is, now you see the system is insulated. That means electrical resistor is now insulated. Now, you take this system which is insulated. You can ask this type of fundamental question, I will appreciate. Okay, now this is there, work transfer is there, W electrical. W electrical, what is this amount? This is minus 2500 as already we have calculated, joule. But what is Q? So, according to first law, 0 is equal to delta U minus 250. Now, you see there is a delta U. That means the internal energy has increased, and as we know that delta U is equal to C into delta T, that C is the capital C. I am sorry, that could have been written by mass into specific heat. So, this is the capital C. So, actually this C is m into small c, specific heat. Okay. So, therefore, we can write this is equal to mass into specific heat into delta T according to this relationship. So, then we can write, here I can write 2500. What is the mass? Mass is 0.01 kg, and what is specific heat? 0.84 kilojoules. So, we have to transfer to joule, that means 840 joule per kg K times the temperature difference delta T, that has to be found out. So, this gives a delta T. So, delta T I can write rather straightforward 840 into, let Tf is the final temperature, that means it starts from Ti initial temperature and reaches Tf final temperature, Tf minus Ti. What is Ti? Ti is 300 K, very good. So, if you do this calculation, then you get Tf equals to what? Tf equals to 597.62. you calculate TF will be equal to 597.62. You check, there may be some error here, but roughly it will be 597.62. Now, question comes of delta S. Now, here also I write delta S universe is equal to delta S system plus delta S surroundings. Clear? Now, you tell me first what is delta S surroundings here? 0, because there is no heat interactions of the surrounding. This is surroundings. Now, again, now your question will be better understood that delta S system is there, which is non-zero, obviously. Otherwise, the principle of increase of entropy will be violated. Delta S universe is greater than 0. So, system entropy changes because of the change in its state, which is manifested through this change from temperature of 300 K to this, which could have been possible by a reversible heat transfer. But as because it is an irreversible process, the temperature change is possible even without heat transfer. But in a reversible process, temperature change is never possible without a heat transfer. If temperature change is possible, it is only possible by a reversible heat transfer. Okay, only in isentropic process, temperature change is possible without a heat transfer process, only by expansion and compression process, that is a reversible adiabatic process. That will be again made clear afterwards. So, therefore, this is enough. So, delta S system we can write as I have done earlier, that if I consider a reversible heat transfer process, so this will give mCp dt is the delta Q, because what I am doing delta S system precisely, this is the thing, is nothing but integration of delta Q by T reversible. Now, this reversible process heat addition is mc dt, small temperature difference, you give a reversible heat transfer. So, that magnitude becomes mc dt. So, this will be integrated from Ti to T. This is a very important concept, which gives mc ln Tf by Ti. Now, you see that the change in entropy is connected between the states. So, if one knows Tf Ti, even if the process is irreversible, where the heat has not been given by this amount slowly, but by some means the temperature is changed from Ti to Tf. So, therefore, entropy change is same as whether it is a reversible or irreversible, but to calculate it we will have to use the equation for the reversible process, and it comes mc ln Tf by Ti. Now, if you substitute the values, m is equal to what? 0.01, m is equal to 0.01 kg, proper unit C is equal to 840 joule per kg, okay, K, and Tf already we have found out this, Ti is this, you get, and delta S system is 5.85 joule per K. This is the unit of the entropy change. So, that becomes equal to delta S universe. It's clear?
Yes.
Another thing I forgot to mention you, and sorry, that in the last example, I only solved the heat input to the engine per unit heat output from the heat pump. Another task is there, that is left to you as an exercise. When this 11.1 degrees change to 5.0, that means I am coming back to the earlier thing, that means this temperature will change then, system temperature by 5.1 here minus 5.1. You exercise this thing, is a routine exercise, and you will see that results will be reduced, that means this value will be reduced, and the result will be in this case 0.55. Now, you can ask me, sir, what does it convey? A simple routine calculation, just you change, just like a kindergarten student, just you change the value of 11.1 to 5, but it will give you an idea. That means, if you go on reducing this temperature gaps, this COP is ultimately going close to the, what is that? This value, sorry, not COP, obviously COP is going close to the ideal COP, and this value is reduced. You understand? That means this heat engine will require less heat per unit heat output from the heat pump to the block of flats. So, this value will be reduced. Okay. So, this is the exercise for which the second part, that when it is reduced, the temperature difference is reduced to 5 degrees given, that you can solve. So, these two problems will give you an immense idea about how we can apply the entropy change formula for a problem. There are a number of problems, if I get the opportunity I will solve. Now, I will come to the next section, that availability, available energy and exergy. Before I start, I must tell these things. Very few books write this sentence straightforward and boldly, and sometimes at a very higher stage, I tell from my vast experience, this is being asked at different levels, even at a higher level, at the recruitment level of a senior faculty positions also it is asked that what is the difference between availability and available energy, what is the difference between availability and exergy. These are the terminologies, it will be made clear afterwards, but before that I must tell that these are synonymous terms, just like three names of a person. The same person, identical person, they are called by three names as and when required. In his house, his parents call by certain name, his wingmate called by another nickname, and his professional friends called by another name. It is like that. So, as and when required according to the convention used, we will use the terminology. So, therefore, I must tell these three terms. What these are will be explained afterward, but first you write this availability, this is our available energy, able energy or exergy, the way you pronunciate it, exergy or exergy, EXERG, they are synonymous terms, and sometimes I will be use availability, sometimes I will be use available energy, and sometimes I will be using exergy. I will use this and this depending upon the common convention that is followed. Okay? Now, what is available energy and availability? Now, this comes from this is one of the very important aspects of second law. The way entropy was defined as one of the very important aspects or straightforward consequences of the second law. Similarly, the available energy is another important consequence of the second law. Before that, again I brush up. Sometimes in teaching of thermodynamics, particular thing has to be told repeatedly, 10, 20 times. Again I tell the first law of thermodynamics, if this question is asked, what new information about the quantity energy is being given by the two laws? First law gives the two different status of energy. One is this point function status, another is the path function status. So, heat and work are identified as path function energy, which are only defined in transit between the systems or system and surrounding. But there are energies which are like properties, which are properties of the system, and they are energy with point function property, which can be stored within the system and are ascribed as the system properties, and therefore they are point functions. These are internal energy, and first law tells the difference between the heat and work interaction in a process is that energy which is stored in a system which gets the status of point function. So, first law of thermodynamics gives the birth of two status of energy as point function and path function. But second law of thermodynamics, because I told at the beginning, in this class we are only concerned with the heat and work. So, all first law, second law aspects will be defined in terms of heat and work. So, second law gives a directional constraint as far as the mutual convertibility between heat and work in a continuous cyclic process. What is that? Heat can never be converted completely into work continuously in a cyclic process, whatsoever the cyclic process may be. Even in an ideal case you cannot do it, but work can be continuously converted into an equal amount of it. That means this gives the directional constraint. So, if you write this second law concept on the constraint of mutual convertibility of heat and work, I can show it like that, that if heat is being converted into work in a continuous cyclic process, heat is converted, this is a cycle. Because a cyclic process is required for continuous conversion work, we know that the result is that W is less than Q. Some of the heat energy has to be rejected, cannot be converted, everything cannot be converted. While if you want to convert work into heat, so you can definitely convert the entire work into heat. This does not violate the first law. Apparently, it means it is in accordance with the energy conservation, but it is not. Why? Because some portion of heat is still left here, Q rejected. So, this is the basic foundation on which we define the two grades of energy, high grade What is the definition of high grade energy? High grade energy and low grade energy. Do you know what is then high grade energy? High grade energy is that energy, do not tell that it is work. Again, high grade energy is that energy which can be continuously converted into low grade energy. But low grade energy is that energy which cannot be continuously into high grade energy. If you make the two energy now in transit, work and heat, you see that heat cannot be completely converted into work, whether work can be completely converted into heat. This is the reason for which work is defined as high grade energy, whereas heat is defined as low grade energy. That means the low grade energy can never be converted into high grade energy with an equivalent amount, whether the reverse is true. But this is not always true for heat energy. There are other forms of energy, as I told, that energy stored in a system, internal energy. You know there is a point function. Now this internal energy, again we come back to the earlier discussion, have two divisions. One is the mechanical form of internal energy, that is kinetic energy, potential energy. If you leave aside that form, what are the other form of internal energy? Is intermolecular energy. Okay? That is because of the temperature of the system, because of the chemical bond energy of the system. If a fuel, you know that within a fuel there is an internal energy, which sometimes we ascribe as chemical energy. When you will come to the thermodynamics of reactive system, these things will be clear. These are all internal energy stored within the system. So if you keep aside that mechanical form of internal energy, that means kinetic energy and potential energy, then we are left with this intermolecular energy, which are manifested through its temperature, the chemical bondage energy, that chemical energy. This energy is stored within the system as a point function. These energies are also low grade energy. If you want to convert it into useful work, the full amount you cannot convert. So this will be conceived this way, slowly it will come, that if a system is at an elevated state compared to its surrounding, I have told, when the system properties are exactly same with that of the surrounding, the system is known as a dead state. That means system cannot perform any process with the prescribed environment or surrounding. But if the system is an elevated state, because of its stored internal energy from that of the surrounding, always an opportunity exists to develop some work while the system is allowed to come into equilibrium with the environment. So in that process there is an opportunity to deliver to get some work, but that work can never be equal to the total stored energy within the system. So therefore that is why the stored energy within the system, apart from kinetic and potential energies, are also termed as low grade energy. So henceforth you must know that low grade energies, either the energy in transit or the energy stored in the system, are those forms of energy which cannot be completely converted in a cyclic process by an equivalent amount in the form of high grade energy, if there exists such type of energy which can be converted the reverse way with the other form of energy. And in fact work is that energy which is the high grade energy, which can be completely converted continuously either in heat, which is the transit form of energy, or in the stored internal energy, which is the point function or stored form of energy. So that is why work is high grade energy, and heat and the intermolecular energy stored within the system is a low grade energy. All right. So then I tell you a thing, that this we can now show like this: low grade energy, low grade. This is the information. First I tell you the information, then logic and deductions will come. Information is very important. Low grade energy, especially nowadays, day of information technology, information generation, information, these communications, all these things are very important. Low grade energy, which comprises heat, this is a transit form of energy, or intermolecular energy, stored intermolecular energy. If you want to convert this, continuous conversion through a cyclic process, then we will see that we cannot have the entire energy converted. There is a restriction, there is a maximum amount work that can be obtainable, maximum amount of this energy obtainable as work, that is the high grade energy. So, obviously, these two are dependent, a minimum amount. So, there is a minimum amount when this obtainable work, there is a maximum, that means a maximum conversion is possible as work, which means automatically there is a minimum fraction or minimum amount left as what? Low grade energy, very good, left as low grade energy, and this we defined as available energy or exergy of what? Of this energy. Similarly, this is known as non-available energy, non-available energy, I am not writing this full, and energy. These are the terminals. That means there is a minimum part which has to be rejected and there is a maximum part. This is the second law, this is an axiom which can be converted. That means this available energy of this low grade energy symbolizes the work potential of the low grade energy. Then what is the work potential of the low grade energy? That means low grade energy has this work potential, that means that is the maximum amount of work which can be extracted from it under any circumstances, even in the ideal case. This is an ideal criterion, whereas there is a minimum amount which has always to be left as low grade energy. So, this is known as what? This serves as an work potential. This is another terminology, but not very frequently used. This is the work potential of, these are all ascribed to this, but here one thing has to be understood, very important. These are all referred to a surrounding. These are all referred to a, why? Because what will be the maximum work obtainable from a given low grade energy at a given prescribed state? That means if I tell heat from this thermal reservoir, because it is heat in energy in transit, this is the intermolecular energy stored in a system which is prescribed at certain state. Then if this question is asked, what is his work potential or what is his available energy, availability, exergy, that is the maximum work that can be obtainable in an ideal system. The next question will come then with respect to which surrounding, because surrounding is very important. Surrounding has to be prescribed, because you know the Carnot's efficiency does not depend only on the thermal reservoir where heat is being taken, it depends upon the temperature of the thermal reservoir where heat is being rejected. So, with respect to a given surrounding, these values depend. So, that available energy or exergy, that is work potential of a low grade energy, is defined when the low grade energy and its state is prescribed with reference to a given surroundings, which is sometimes known as available energy or exergy reference surroundings or environment. This information is clear to you?
So please repeat the last part about surrounding.
Surrounding, this is because last part of the surroundings I explained that the maximum work that is obtainable from this low grade energy will depend upon the surroundings. For example, I am telling you have an elevated system, that means that some pressure and temperature or some property with reference to a surrounding. So, the maximum work that you can get from this system, there is an opportunity of developing work till the system comes to dead state, that depends upon the surrounding. If I tell a system at this pressure, temperature, volume, and if I tell that what will be the maximum work can be obtainable before it comes to dead state, today is much different what it could have been done in the first week of January when the ambient temperature was 4-5 degrees Celsius. So, you can very well understand. So, the ambient plays a major role, that will be again clear afterwards. Now, let us first find out heat in transit, heat. Now, I take it. Now, let us consider that heat is available from a temperature reservoir T1. Now, you tell me, if I pose this problem that heat is available Q1 at T1, what is this maximum work obtainable? We know that for maximum work we have to use a reversible engine, that is Carnot's engine, reversible heat engine. That means we will have to search for a sink where the heat has to be rejected, because otherwise we cannot get the work. let this sink temperature T2. We know the work, maximum work is of this given heat at this temperature Q1 into 1 by 1 minus T2 by T1. What is this? This is eta Carnot. This is clear? Clear? That means, you see one thing, that now you see this is the efficiency. So, for a given heat input to a engine, the work developed depends upon the efficiency, and efficiency is maximum for a reversible engine. So, this maximum efficiency depends upon T2, T1. More is the temperature, for the given heat input, more is the efficiency, more is the extraction of work. Similarly, lower is the sink temperature, temperature of heat rejection, more is the efficiency and more is the work extraction. Therefore, our main motto will be to have a higher temperature and a as low as possible sink temperature, heat rejection temperature. Now, if this temperature is prescribed, that means we know a temperature T1 where from we have Q1. That means Q1 of amount of heat is obtainable from the temperature T1. Then we will have to search for the minimum T2 available so that we can get the maximum work. What is the minimum T2 possible without any other effort? That is the ambient temperature. Very good. Which is commonly symbolized as T0. So, the ambient temperature. So, if that is true, so the maximum work is Q1 into 1 minus T0 by T1. So, therefore, you see the surrounding comes into picture. So, depending upon the T0. So, for the same amount of heat Q1 at T1, the availability here will be much less than the availability very close to the poles, because there the T0 are very less. Okay, so therefore, the ambient comes into picture in this simple example. Now, you see, if therefore, you see that this W max, this is the available energy. So, I write available energy of Q. Now, this I now available energy of Q1, available energy of Q1 at T1 equals to Q1 into 1 minus T0 by T1 with reference to a surrounding temperature of T0. That means, this we can take here also, available energy of Q1 at T1 with reference to a surrounding temperature of T0 is this. All right. So, now the available energy depends both on the surrounding and on the temperature from which Q1 is obtainable. Now, you see that, now if you consider that let T0 is fixed, ambient temperature, that is ambient. Now, instead of getting the heat from T1 temperature or delivering the heat from T1 temperature to the engine, I deliberately want as a designer, as an engineer, that this heat I will first transfer to a lower temperature. There may be some difficulties also. The heat engine is unable to accept this temperature. There is some practical problem where heat engine cannot take heat from that. I just transfer it to by a natural process, means T1 greater than T2. And this same heat is now given to the heat engine, consider a reversible heat engine, to the heat engine at T2, and it rejects the heat. Now, here you see, sorry, this is the heat rejection Q2. So, what is Q2? Q2 is Q into T0 by T1, because this is Q1, Q1 T0 by T1 is the heat rejection. This is the unavailable energy, able energy. So, therefore, you see Q1 comprises of two, one is the available energy plus the unavailable energy. So, available energy is this plus, so Q1 is available plus unavailable energy. Now, you see what is available energy of Q1. Now, what is available energy of Q1? Now, at T2 with reference to T1, this is all right with reference to T0. What is this? You tell me. This available energy is Q1 into 1 minus T0 by T2. It is lower than the earlier one. This available energy is lower than the earlier one. What was that? If it was taken from T1, it was Q1 into 1 minus T0 by T1. Now, T1 is greater than T2. So, therefore, this available energy is lower than this. Clear? That means, when same heat is taken from a lower temperature, its available energy or work potential is reduced. So, therefore, it is always advisable to accept heat as high as possible thermal reservoir. That means, if the temperature is rejected, is available energy or work potential is reduced. That means, it is not only the amount of heat which is important, but it is the temperature of the pot or thermal reservoir where from heat is coming, it is important, provided the surrounding is fixed. Okay. So, therefore, always it is advisable that heat should be taken from the temperature which is as high as possible. So, this is the basic concept of available energy or availability of heat, the energy in transit. Okay, today up to this, thank you. Next class again I will continue.